It's a pleasure to chair this particular session. Tom Malkin is going to tell us about minimal complexity assumption for cryptography.
Okay, hi everyone. So this question I've been asked many times in the past few days. What are you going to talk about? And I still don't fully know, but let me quote what I was asked by the organizers to do. They wanted me to survey the basic concepts and main open questions in cryptography, as well as what is known with black box reductions, etc. Okay, and the key point is to make it accessible to all serious program participants and therefore boring to the experts. That's what I was asked to do. Now, I want to say it's clearly impossible to cover everything. In general, it's impossible. And also, given the answer that I gave to this email, which is, I will have extremely little time to prepare the talk. Do you still want me to talk? And they said yes. So nonetheless, I'm going to try to address some non-empty subset of these things. And I would like you to help me make it accessible and boring and ask a lot of questions, okay? And discussions and answer the questions, etc. What am I going to talk about? So first of all, I also wanted to add, so this is like a survey, I don't know, of everything. Everything from, if you were here in Raphael's talk, everything like from here and to the right, if you remember from Raphael's talk. Definitely not attempting to be complete, and it's very biased sample. It will not be heavy on proofs. There will be hand waving. I'll give a bunch of definitions, but not super formally. And there'll be lots of colors. Raphael said he doesn't like many colors. I don't usually either, but this one has a ton of colors. It's very retro. A bunch of the slides are from my job talk and other talks in the 2000s. And even then there was a retro 80s disco vibe, you will see. So that's, I don't necessarily recommend you do talks like that, but this is what it is. What else? I'm going to start with stuff that's really old and experts definitely know it. And then later I'll talk about some open problems that I would be happy to work on. My goal is to give like some overview and some ideas of things that are interesting, open problems that are interesting, if you want to talk to me about them or to each other. Okay, that's what I'm going to talk about. I know it was vague and unclear. Hopefully it will become clearer. Okay, so cryptography in the last 2,000 years. See Raphael's intro. So this is for real. I know this is recorded. If somebody's just watching this recording, you really should go back and see like the very beginning of Raphael's talk is exactly the introduction I was going to give to cryptography in the last 2,000 years. So happily, I don't need to do it. And what I will really talk about is about assumptions in cryptography. So here is the narrative that often is being told, and indeed it's true. And we've seen it several times in Raphael's talk and in all the other talks and several other talks. All the talks, I think, so far touched upon these things. For most cryptographic tasks, we cannot hope to give unconditional proofs of security, as they would imply, the collapse of the hierarchy. They would imply that NP is hard on average, which we don't know how to do. So first of all, people always say it's not quite true. There's definitely a lot of rich and beautiful information theoretic cryptography, which was also mentioned here, I think in Rahul's talk. Right, there's lots of stuff that you can do information theoretically with no assumptions. And there's some examples here that came up in a bunch of them, like secret sharing and one-time encryption. They already came up in a previous talk. These information theoretic things, they tend to be, so why I think both narratives are correct, that everything in cryptography requires one-way function, and yet there's a lot of cryptography information theoretically. I think the information theoretic things tend to be either multiple parties, and then maybe some of them are honest or something like that, or things that are for limited number of executions, or like there's non-malleable code example here. You don't need to understand all of these things. I'm giving an overview. I think there the point is the adversary is weaker than the good guy. So there are some settings in which information theoretics suffices. However, this will not be our focus today. And so I'm going to continue with the narrative that we must make some assumptions. So let's talk about which assumptions we can make and how to minimize them. Okay, please do interrupt me. I would love it.
The point is that anything that is not information theoretic needs a minimal assumption that is hard.
Yeah, but I agree with that. But that's almost by definition, right? If it's not information theoretic, then it needs an assumption.
No, but I'm saying that the one-way function will be a minimal assumption.
Exactly. Okay, I agree with this point. So let me repeat it. Anything in cryptography that's not information theoretic, as far as we know, maybe in fact you could find some weird counterexample.
Zero knowledge in IO.
I'll talk about IO. IO does not require anything, but I will talk about it. Anyway, the spirit of what Amos says is definitely true. One-way function is necessary. Okay, so, but anyway, I actually didn't say anything here about one-way function. I was just making the point that we have to study assumptions and see what they are. So there are barriers. Ideally, we would like to prove it based on, I don't know, NP is hard on average, but there are barriers that Raphael mentioned, other talks mentioned. I think we didn't see any talk that really goes into those barriers. That would be interesting in a future, maybe in the crypto workshop that will be at the end. I don't know. It just sounds to me very interesting to discuss more the barriers. But instead, people make concrete assumptions, like from number theory. There's a list of assumptions here. You know, factoring is very famous, but they're also like AES is also an assumption. We heard a lot about Kolmogorov. There's a bunch of assumptions that people make. Good. In this talk, so why do we trust these assumptions? Because many people worked on it, they tried hard, etc. I think you know this narrative. On one hand, there's some tension. On one hand, we want more assumptions. It's better to have more assumptions in cryptography, more sources of hardness, because what if what we already have turns out to be false? Like, I don't know, factoring is broken by a quantum computer. What if other things will all be broken? So it's good to have a lot of sources of hardness. On the other hand, we want to unify the universe. We want to have as minimal assumptions as possible. We want to have assumptions, few assumptions that people can really work very hard, and therefore we gain confidence in them. So the way we negotiate this, and my focus on this talk will be to focus on cryptographic primitives. So I will not really talk about lattices or any of these things written here. But in fact, I will talk about cryptographic primitives, and then these primitives can be instantiated, different primitives with different assumptions, or sometimes with the same assumptions. And then if the assumptions is false, we could still try to instantiate the same primitive with a different assumption. Okay, so this is the point of view in this talk. I will focus on cryptographic primitives. Yeah, so this is what we want to do. I'll say which cryptographic primitives, like one-way function that came up, but also other ones. Good. I don't think I need to convince you that it's interesting to study reductions and understand implications. So this brings us to Impeliatsu's worlds, which were mentioned in every single talk many times, and rightfully so. That sort of tries to bring together this idea. This is a picture from Marshall's, from his job talk, I guess. Was it from your job talk? I don't know from what, that he allowed me to use. What?
It was in my job.
It was in your job talk. Okay. Anyway, these are the 5 worlds. Raphael and others talked extensively about all the way through Minicrypt, one-way functions. I'll talk more about them. And then there's Cryptomania, where public key cryptography exists. Raphael added another world on the left. I'll add another word on the right, but it's not mine. It's another world that people have suggested after in the last 10 years, which is a world where you can be your best self and have the best life you can have. Everything is possible. A world is called Opustopia. I tried to, this is me trying to finagle Marshall's drawing, but I'm not as good. I'm trying to imitate his handwriting. Anyway, this is Opustopia, where we have, in addition to public key cryptography, also indistinguishability obfuscation. So I will try to talk about what we know about assumptions in these worlds and what can be done, etc. Good. Any questions so far? Yes. First of all, yeah. So I love this question. I can convey the question to somebody else in the audience who will answer. Marshall, what is the meaning of the picture for Pesilan? All right. Good. Yeah, it's pestilent because everything, right? Easy is good and hard is good for cryptography or for algorithms. In pestilent, it's like easy, but not easy enough, and hard, but not hard enough. It's terrible. Okay.
Why do you say PKE plus indistinguishability obfuscation? I suppose if you just say indistinguishability obfuscation,
Good.
that does exist if P equals to B.
Exactly. That's exactly the
Why
reason.
don't you say P not equals B plus indistinguishability obfuscation?
Okay, this is a good, why don't, so good. First of all, I want to say this is a great question. So P not equal, so the question was, why do I define, so I'll maybe let me, okay, I'll answer now and I'll answer again when I get to it, to Opustopia. Why do I define Opustopia as PKE plus indistinguishability obfuscation? One could just say indistinguishability, you know, like in Cryptomania, I didn't write public key plus one-way functions. I just wrote public key. Why? Because public key implies one-way function. So it's enough to write it. Here in Opustopia, it's not enough to write indistinguishability obfuscation. I'll talk about it because it's in fact does not imply the previous one. So Vinod, the simplest answer is I just wanted it to be obviously clear that they are growing in complexity without any problems. I'm trying to present a picture that's like simple. Amos, you ask later when I talk about it. I will leave time for discussions among the audience. So I wanted to start by, this is also something about the overview of my talk. I wanted to start by presenting a very clean picture. And then immediately after, I'll say the picture is highly unclean. There are many complications going on. That's my next message. This page, I still wanted the picture to be clean. So this is clearly more than the previous one. It's everything in the previous plus one more. We could say indistinguishability obfuscation plus NP is hard on average, and that in fact, if you ignore some infinitely often, I don't know what, is in fact the same, but I will say more about it. Good. Now, by this point in the boot camp, you should know what one-way functions are, but if you don't know any of the other words, it's fine. Here's more words. Okay, so these are a bunch of known reductions, implications. So there is a if and only if, or an implication if there is a reduction, I guess a Turing reduction, but I'm not very precise. I will not be very precise, but this is the classic perspective on how people describe these things. It's also correct when I say classic perspective. Today, the perspective is shifted a bit, but still I'm not lying in anything I'm saying. So in Minicrypt, the idea is there's a ton of primitives. There was a big body of work and it's all very pleasing and beautiful. It's all equivalent to each other. One-way functions, if and only if pseudorandom generators, pseudorandom functions, digital signature schemes, private key encryption, and more things. It's all very neat and tight and equivalent to each other. And that's Minicrypt. So the red ones are the ones that Impaliatsu chose to highlight in his definition of these worlds. He defined Minicrypt as one-way function, but no key agreement. In Cryptomania with key agreement and no one-way function. I'll define a lot of these primitives like immediately soon in this talk. Okay, so, and these are different primitives that imply each other. So we know, I don't know, trapdoor functions imply public key encryption, etc. There's all kinds of primitives going on. I'll show you this picture again after I define some of the primitives. Okay, so this is still kind of clean picture. My message would be that the picture is really a lot more messy and there are many interesting things that happen. Good. So one-way function, you already know. Let me just write the definition. This is, we've already seen the definition. I will just, F is a one-way function if it's efficiently computable, but hard to invert. The font seems a little weird, but okay. But hard to invert. So I'll just highlight that it's an average case, obviously, definition. So you choose an input at random, you compute f of x, you give it to the adversary should not be able to invert it, except with negligible probability. And there are variations like Raphael discussed, weak one-way functions, etc. Okay, and from one-way functions, we can construct private key encryption, which I will not define formally, but I'll just say, you know, it's the standard notion of encryption. Alice and Bob agree in advance on a secret key, and then they can send messages to each other. I'll define public key encryption in a minute. Okay, so this is one-way function. In this, but this picture that I showed before, this is sort of the reason why everybody says you need one-way function as the bottom thing, and everything implies it. Good. there's also trapdoor functions, which are very similar to this. This is a highly non-formal definition, but I think it's good enough. You can sample from the function, and then it's easy to compute. You can sample a function, it's easy to compute on any x, but it's hard to invert. It's a one-way function. But given a trapdoor, it's easy to invert. Okay. Oh, by the way, I didn't mention, because my talk is not focusing on specific assumptions, but just to give an example, I don't know, for one-way function, an example is, g to the x mod p, like for discrete log, or SHA. These are examples for candidates that we believe are one-way function. Okay, but anyway, I will not focus on the concrete assumptions. Okay, so that's a trapdoor function. You can also consider trapdoor permutations, which are where f is from d to d, from the same domain to itself. Okay, it's important that they're enhanced. I didn't want to define what it means exactly. Unless if you want me to, I can. It won't be important for my talk. Okay, but it's important for what I wrote on the slide to be actually correct. Basically, enhanced trapdoor permutation is that you can sample from the image without actually knowing the pre-image. Okay.
For the functions, there's no restriction on the number of pre-images, or because otherwise it's equivalent to one functions, no?
It's poly to one. Is that what you're asking? So yeah, it has to be poly to one. If it's not poly to one, I don't know if that actually addresses what you're asking, but it has to be poly to one. There's no restriction. Why is it equivalent to one-way function? It's not. Well, I don't know.
Looking at trapdoor functions, if there's no if justified that way, there is this it's homework problem, yeah.
It's observation of meet and et al, right?
Yeah, it's
no, but that's
publicly be let the publicly be a favor, and then you always let the or be a pre-image to you can always invert the public key.
So, Raphael,
I think the poly to one is what solves this, right?
Yeah.
I want to find some example.
Yeah.
You're saying that something here is wrong in this implication? You're saying that trapdoor functions don't imply public key encryption? Is that what you're saying?
Well, maybe if you add that poly to one thing, yeah.
Poly to one, yeah, I am adding the poly to one. Sorry.
Okay.
I thought you were arguing that even that is not enough.
No, yeah.
Yeah, it has to be poly to one.
So
Yes.
what's the statement again? If you only have exponential to one,
If you just have that
then
definition, that's
you
there.
can get it from one-way functions.
Yeah, because you just say that you can have an extra pre-image, which is just if you can invert the public key, that allows you that gives you like a dummy trapdoor pre-image.
You're saying from one-way functions, you can get trapdoor functions that have exponentially many pre-images.
Yeah.
Yeah, right. The definition should be poly to one.
You're saying if I know or, then output to the second part or something like that. Yeah.
Yeah. Right. Good. It should be poly to one, but still it's less structure than trapdoor permutation, say, right? Or regular trapdoor function. Good. Yes, please.
Just be clear, what's the definition of poly to one?
Oh, the size of the pre-image. I guess that the size of the pre-image should be polynomial. So you know what one-to-one is. Poly to one, polynomial in the length of x, so an input of length n bits. There's only polynomially many inputs that map to the same output.
I see, and that's worst case, right? For all.
It's worst case, but in all of these definitions, if you have a tiny fraction, so I think it's fine even if it's not worst case. But let's define it to be worst case. I mean, the typical example, for example, is, I don't know, squaring mod n, which equals p times q, something like that. So if you know the factorization, you can invert. That's like, I don't know, 4 to 1. Okay, so Public key encryption and key agreement. Sorry that this now it's almost done. There won't be many. There's a bunch of slides that just tell you something about the primitives, so we can talk about them more in a more informed way. Good. So public key encryption, I drew it as a communication just because later I'll talk about, or not later, in the next line will be about key agreement, which will extend it to many rounds. Public key encryption, you can think of an algorithm, a protocol with 2 rounds between Alice and Bob, where Alice sends a public key and Bob sends an encryption of a message. Importantly, it's randomized. So it's a triple of algorithms, GED. G is a key generation algorithm that takes randomness and gives you a public key and a secret key. E encrypts. E gets the encryption gets public key, message, and randomness and gives you a ciphertext. And the decryption algorithm can recover the message from the ciphertext. This is the correctness definition. And the security definition is that any adversary, any passive adversary that sees everything on the line, so given PK and C, does not learn any information about the message that was encrypted. Okay, and this turns out to be equivalent to saying that the distribution of an encryption of one message for any 2 messages, distribution of encryption of one of them and the other one of them are indistinguishable. Okay. And finally, key agreement is exactly the same thing, but in many rounds. So there's Alice and Bob, and they discuss for many rounds, and then they agree on some, maybe it's not obvious that it's the same, but it is, that key agreement in 2 rounds is public key encryption. They discuss for several rounds. At the end, they have to output some key. This is the correctness. And the security is that no adversary that sees the entire transcript can distinguish the key from random. Good. Any questions? Okay, I wanted to make a note about trapdoor function versus public key encryption. They seem very similar, and I just wanted to put it out there that you can think in some intuitive way, in some moral way, of a trapdoor function as a stronger de-randomized version of public key encryption. Okay, why do I say that? In trapdoor function, the task is from the output, so that in trapdoor function, the key generation algorithm gives you, I didn't specify it formally before, it gives you index to the function k and some trapdoor, and then you can compute f of x, but it's hard to recover x without the trapdoor, and it's easy to recover x with the trapdoor. In public key encryption, the encryption algorithm takes m and randomness r and gives you some ciphertext c, and then going from the ciphertext C back to the message is easy if you have the secret key. But notice that we don't have R, we cannot recover R necessarily. So you can view them as very similar definitions, except this one is randomized. There's a randomness that you might not be, the decryption algorithm may not be able to recover. Okay, and indeed trapdoor functions imply public key encryption. Any questions? Okay, I think that was the, oh yeah, there's oblivious transfer and secure computation. That's the last one for now. Good, so this is oblivious transfer primitive. Sorry, let me stop for a minute. Anybody has any questions? Okay, so OT, oblivious transfer, defined by Rabin, or I guess some similar version was defined by Rabin. Alice has, so again, this is not a formal definition. You can define it with ideal world, etc. This is not a formal definition, but the idea is the following. Alice has 2 secrets, S0, S1. Bob has a bit B. They get involved in some correspondence, and at the end of the day, Alice gets absolutely no information about anything new, and Bob learns SB. So Bob can, this is oblivious transfer, Bob can choose either S0 or S1, whatever he wants, and learns nothing at all about the other one. Okay, so for example, if these are bits, he can only guess them with probability half, plus negligible. Okay, that's called 1 out of 2 OT. And you can think of it as secure computation of this specific function. You know, f of S0, S1, B equals bottom and SB. So this is a super powerful primitive because it allows general secure computation If you assume you have secure implementation of OT, you can get secure computation of any function. Good. Any questions?
So that's for passive adversary.
Yeah, that's, well, so you can define, this definition doesn't have anything formal. You can define OT against an active adversary and against a passive adversary, but let's keep it passive. Somehow, you know, I drew this picture and before, which I'll show again. There are there are many kinds of secure computation, many kinds of OT, adaptive, non-adaptive. Let's assume the simplest version that everybody's passive. Yeah.
Did you define secure computation?
No, here I am. Here's secure computation. Here's what secure computation is. So you can view oblivious transfer as secure computation of a specific function. In general, secure computation, again, let's think about in the passive case, like you asked, there are n parties, 2 or more parties. Each party has an input xi, party I has input xi, and they want to compute some function of their inputs. Okay, or f of x1 to xm, and each party needs to get some output. Okay, that basically captures almost anything you can think about. Okay, and the idea is, what do we want to do? We want to be able to achieve it securely. What is the definition of security? It's fairly easy to define if you only think about a passive adversary. But basically, you want the any adversary that sees everything. Yeah.
What do you mean by passive adversary?
An adversary. So, given an adversary that sees all the communication that happens. Good. Again, you can define the adversary can corrupt some number of parties, and then he can see everything that they have. Yeah.
But they follow the protocol.
They follow the protocol. They don't. That's what passive is. Yeah. This is just because to make it a little more concrete, you can define it for active adversary that doesn't follow the protocol. Basically, the upshot is this: you can achieve secure computation for any function. There are upper bounds and lower bounds for active adversary and passive adversary, how many parties they are allowed to corrupt, etc. You can achieve this even information theoretically, but then you have to assume honest majority and more assumptions. With OT, you can do it even for 2 parties, like Alice and Bob, yeah, and achieve secure computation. So this was a definition of some of the primitives here. What I wanted to talk about, so it's known, all these implications are known, and this is very old stuff, meaning I guess there's a bunch of new things that happen, and the E is like not that old, adding the noticing that you need enhanced. There are many, many things going on there that I'm not going to talk about. But somehow this is the classic perspective. This is the picture. Good. So it seems intuitively clear and obvious that, I don't know, public key encryption is harder than private key encryption, right? So, and in general, all the things in Cryptomania seem to be harder than all the things in Minicrypt in some intuitive way. It seems clear, both in terms of efficiency often of constructions we have, but also in terms of assumptions we have, and also just in terms of a gut feeling, right? Public key encryption, you need to be able to you know, send some secret message to somebody over a public channel without ever meeting in a secret alley. It seems inherently harder. But what does it, so we want to prove something like that. We want to prove that it's actually harder. Okay, but how would we separate these things, right? What does it even mean? This logically, it doesn't quite make sense to say that it's harder. First of all, they all might not exist. So they all might be false. Like, I don't know, maybe we live in Algorithmica. But even if we live in Cryptomania and they all exist, then in which way is this easier than that? They all exist, right? So in some logical way, it's not clear what it means, right? How can you say A doesn't imply B, right? You could always, if both A and B exist, you can always construct B. Here's a reduction. Don't use A and just construct B, and it exists, and therefore it's great. Okay, so Impagliazzo and Rudish in '89 suggested the approach of proving separation via black box reduction. Okay, so I wanted to say a little bit about that. Okay, so they eliminate black box reductions. I'll say a little more about that. Yes. Previous slide or next slide?
Then you hope to get like equivalence at the top.
Yeah, so I think at that point, I don't know, in the, when was it, 89 in Rudish? I would guess that in 89, the hope was to get equivalence, or, you know, Russell defined 5 worlds. I think somehow, maybe, I don't know what, I don't want to speak for him, but the hope was to have a lot of it, like 5 worlds, and in each world, everything is tight and all equivalent to each other. It would be nice if they're all equivalent to each other. I think that was the, and for some specific implications here, it was more of people, for example, Trapdoor function and public key encryption, people did basically treat them as the same somehow intuitively. I'm not saying, and nobody claimed this in a paper, but people treated them as basically the same thing. And, you know, most public key encryptions we know are based on, although not all, are based on assumptions that come from Trapdoor functions. But not all, like in El Gamal, you don't have a trapdoor there. So I would say it would be nice if they're all equivalent, but as a spoiler, there will not be. Yeah, that's part of the, like, how it's not so beautiful. There's like, which is also interesting. There's a lot of interesting stuff going on. Good. So let me say something about black box reductions. Okay, so also, again, each of these things, slides, is like I could give a whole lecture in a class on. So I apologize for not giving many details, but hopefully we'll give something. So a black box construction of a primitive B from A intuitively is like you construct the primitive B from A using only its input-output behavior. But even more importantly, the proof of security is also black box. So there are many versions of black box, and there's a paper by Reingold, Trevisan, and Vadan who discusses all of them. I would recommend to read it if you're interested in black box reductions. For me, black box is what they call fully black box. That's what I'm defining here. So importantly, the proof of security also needs to be black box. What is a proof of security? Recall when I construct a primitive B, I don't know, maybe I'm constructing a public key, trying to construct public key encryption from private key encryption, say, I don't know. So B uses A in a black box way, but then how do I prove it's secure? I prove that, oh, if you had an adversary for B, then I can use it to construct an adversary for A, contradiction. So we want that part to also be black box, okay? That's what black box reduction is, fully black box reduction is. Good. And most reductions that we know, I can say something about exceptions in a minute, but most reductions that we know are black box in cryptography. So given such a black box reduction, it turns out to be relativizing. Not turns out, it like follows directly, that it's relativizing. What is a relativizing reduction? It means that if you prove that A implies B using a black box reduction like this, so if A implies B, then A would imply B relative to any other oracle as well, if your proof is black box like this. Right? Good.
Everybody has access to Oracle.
Everybody has access to the Oracle, yeah. So yeah, so here you see, yeah, you see the adversary has access both to the original A and to the adversary for B, and the adversary for B has Oracle access to A. Yeah, so our reduction is black box if this happens, and this implies in particular that it's also relativizing, that it's true with respect to every oracle. Good. So following this is in Pagliaccio and Rudish oracle separation paradigm is the following. In order to show, for example, that private key encryption is easier than public key encryption or any two primitives, their idea is this: you construct some oracle gamma, then you prove that relative to gamma, primitive A exists. So that eliminates the whole issue of, well, we don't know if this exists in the first place, or maybe they both exist, etc. So the idea is construct an oracle gamma such that relative to gamma A exists, but B does not exist. Okay, this immediately proves that there's no relativizing reduction of B to A, and therefore also no black box reduction of B to A. And therefore, I'll say more about therefore in a minute. Okay, that was their suggestion. Good. And using the suggestion, they proved that there's no black box reduction of key agreement to one-way function. And I wanted to give you a very little small idea of the proof of this, okay? Just to give you an idea how it works. Good, let me see. So I'm reminding you, what are we proving? We're proving that one-way function does not imply key agreement in a black box way, okay? And we're gonna follow this idea. So the oracle they choose has two parts. One part A is a completely random function, chosen completely at random. And one part B is a p-space complete oracle, or any oracle with respect to which P is equal to NP. Okay, why? We'll see in a minute. So as a first step, they prove that the oracle A is a one-way function. Okay, what does it mean that it's a one-way function? So a truly random function that you have, you cannot invert in polynomial time. And in fact, you can even prove that you cannot invert it even in exponential time, as long as you only access the oracle polynomially many times, you cannot invert it, except with negligible probability. Okay, that's not too hard to prove.
This is even given the B oracle, right?
Good, exactly. So first, let's start, yes, exactly. But let's start with just A. So this is not so hard to prove. But now we added another oracle B. I'll get back to it in 1 second. Additionally, this is the hard part. The previous was not so hard. This one is hard. You want to prove that there exists no secure key agreement protocol relative to this oracle. So let me see, maybe let me write something. Maybe use the board, it might be easier. So what do? There's, Alice and Bob. There's Alice, Bob. And let's assume there was some key agreement, supposed key agreement protocol. Both of them have access initially to A. I will add B in a minute. Okay, A is a truly random function. So we know it's a one-way function. They both have access to this. And now we want to prove, the next step wants to prove that there exists no such protocol that is secure against Eve as follows, against an adversary that gets this whole transcript. So the adversary Eve gets this whole transcript and tries to figure out the key. At the end of the day, Alice and Bob agree on a key as an output of this interaction. So initially at this point, good. Let me assume that Eve is exponential, unbounded adversary. Okay, I'll make Eve bounded in a minute. Eve is exponential, unbounded adversary, can work as much as she wants, exponential time. However, Eve is only allowed polynomially many queries to A. Okay, in this regime, they first prove as a first step, maybe they didn't phrase it like this. This phrasing is more along the lines of Barak and Mahmoudi. But this is basically what they did, just phrased in a more modern words. Here's what Eve will do. There's a way for Eve to look at this transcript and figure out what the key is. How will she do that? Here is a rough idea. First, let's assume if Alice and Bob in this protocol never use the oracle, then definitely there's no secure key agreement because Eve is exponential, is unbounded. There is no unconditionally secure key agreement. So they must have used this oracle. That's the only bound for Eve. The key agreement, I didn't say it explicitly, but when I said all of these things in crypto require assumptions, it's not hard to prove. So that key agreement cannot be done information theoretically. Good. So they must have queried this A. Okay. Moreover, if Bob and Alice queried this A and they can query on whatever they want. If they queried on all queries that are not the same in Alice and Bob, they don't really matter. I mean, all of this needs to be proven. So if they manage to agree on a key, somehow, well, either Eve can figure it out, but if Eve cannot figure it out initially, it means that it came from the oracle A. So what they do is they show how to, what Eve does is she keeps sampling transcripts that are consistent with what she saw so far. And if this transcript require Alice or Bob to query the oracle, Eve queries the oracle and corrects the transcript, something along these lines. I'm obviously not giving a full proof. Okay, but at the end of the day, she can sample enough transcripts so that Eve also query the oracle A in all important queries that are joined for Alice and Bob. Okay, and therefore she can figure out K. I don't know if this is convincing, but this is the general idea. It's very nice. Okay, once you do it like this, so now I know there is no key agreement protocol secure against exponential Eve that has only polynomially many queries to the oracle. Now they show that if they add B here, which is a p-space complete oracle, that's the next step. You add B here, so everybody has access to it. It's a p-space complete oracle with respect to which P is equal to NP. Now they show, first of all, what Vinod said before, that A is still a one-way function. A random function is still a one-way function, even if P is equal to NP. Okay, that's again, not too hard to prove. So first they need to prove that it's still a one-way function. So even with respect to both of them, even though Alice and Bob can now solve SAT, they still cannot invert A. And then that's one. And then moreover, Eve can now be implemented efficiently because she has access to, she can solve SAT, and that helps implement Eve efficiently. This is the high level idea of the oracle separation. Okay, so from this, we concluded that there exists an oracle. This is the oracle with respect to which one-way functions exist, but key agreement does not exist. Therefore, there is no relativizing and therefore no black box reduction. Does it make sense?
So B is just to make sure.
Yes, exactly. And yeah, B is to make sure Eve can be done in polynomial time because the definition of key agreement is polynomial time. But it's interesting even without this. Yes. Good. Yes. I said all of this. So after that, there are many other oracle separations. And let me maybe say like 2 words. So there are many oracle separations between many different primitives. Many of them follow this paradigm of adding an oracle relative to which one thing exists and the other one doesn't. Let me mention there's some other paradigms that can happen. Let me think whether to mention it or not. I guess let me mention it. I'll mention 2 other paradigms of oracle separations. Or maybe let me 1 second. Yeah, okay. Let me say, here's another paradigm which does not, so this idea proves that there's no relativizing reduction and therefore no black box reduction. You could also flip the order of quantifiers. Here's another paradigm. This was used in GMR. It's a paper of mine with Yael Gertner and Omer Reingold, where it was important to do this, which I'll explain in a minute why. But anyway, another paradigm is this. For any, I'm just flipping the order of quantifiers. For any suggested reduction or for any suggested black box reduction, where somebody claims that some primitive P implies Q, construct an oracle gamma such that P exists relative to gamma, but the suggested construction of Q does not. Okay, so it changes the order of quantifiers. I'm not giving you one oracle with respect to which P exists, but no Q exists. No, maybe with respect to my oracle gamma, there exists. So for example, if I wanted to do this for private key encryption versus public key encryption, which why would I want to? The Impeliacci this thing is better. But just as an example, I would say, well, let me tell you the example we actually did it for. We used this to show, and I'll tell you why it was important. We used this to show that in fact, public key encryption does not imply trapdoor function in a black box way. This is what we wanted to show. And there it was very hard to use the previous paradigm because basically what I told you before, first of all, this is a little surprising because people thought of these as basically the same. But as I told you before, this is sort of a de-randomized version. And somehow if I give you an oracle with a random function, it's hard to prove this separation. So what we did instead is we said, well, give me any, you claim that there is a construction of a trapdoor function from public key encryption. Great, give me your construction. I'm gonna show you an oracle where your construction fails. Okay, so for every construction, there's an oracle where it fails. Okay, that's one different paradigm. And this one more second, and this paradigm does not rule out relativizing reductions. It does not. There might still be a relativizing reduction, but it does rule out black box reductions. Yes.
Such definition of relative to the existence.
So you have, so I guess to give a precise definition, I would have to say what the primitive is, like a one-way function or public key encryption, etc. But so let's say public key encryption is a triple of algorithm GED, right? So I want to say that there exists an algorithm G, gamma, E, gamma, D, gamma. So everybody has access to gamma, both the good algorithms and the adversary. So in order to say that there exists a public key encryption with respect to my gamma, I will show an algorithm GED that can access gamma at will, that implement the key generation, encryption, and decryption oracles. And I'll prove to you that it's the correctness holds, and I'll prove to you security. Now, what is the definition of security? The definition of security is that for any, you can say any polynomial time A, or often it's enough to think about exponential time with polynomial access to the oracle. But let's say for every polynomial time A has access to gamma. For every polynomial time A gamma, A doesn't learn anything about, it's the standard definition. A cannot distinguish an encryption of 0 from an encryption of 1. Cannot distinguish encryption of 0 from encryption of 1. Encryption with the public key, with the gamma. So I think you're asking what is gamma, where gamma comes from. Everybody has access to gamma. The primitive existing is just the standard definition of whatever the primitive is, like public key encryption. And for the trapdoor function, for example, to prove that it doesn't exist, I'll show you a specific adversary that breaks your thing. And in terms of constructions, it usually works as you give an oracle that implements this, that's usually easy. But then you add another oracle that tries to foil this, and then you have to prove that it didn't foil the other one. These proofs are notoriously annoying. They're long and complicated, and yeah.
I was just wondering if it's just enough. It depends on the framework. In logic, sometimes it is used slightly differently. Is it enough to assume that gamma exists?
It's not that I assume that it exists. I prove that it exists. And I construct gamma.
No, it says relative to gamma, something exists. So is it enough to assume that gamma exists?
I see. Gamma, it's not like I assume something about gamma. Gamma is something, for example, gamma would consist of a random length tripling function. Okay, I tell you what will be in gamma. The gamma might have a random length tripling function and might have another function that inverts it. Okay. Good. This is one kind of different oracle separation, and there's a completely other, there are actually many other kinds of oracle separation. There's another oracle separation that doesn't rule out things, but rather counts, rules out, gives a lower bound on efficiency. Something like, oh, in order to create this primitive from that primitive, you have to use it at least this many times. Okay, if it's a black box construction, or else, I don't know, I would manage to do the same construction unconditionally, which is a contradiction, something like that. That's another oracle separation. And there are newer Oracle separations. Yeah.
So really the only difference from Ipaliaso Rodish is that here the Oracle depends on the construction.
Yeah.
That's it.
That's the only difference. It also means the result is weaker. It doesn't rule out relativizing reductions, but it still rules out black box reductions. Okay.
Sorry, one more question.
You know,
Are there
please,
any
I want questions.
non-relativizing constructions known?
Good. Are there any unrelativizing constructions known? I think this leads beautifully to my next slide. If I don't answer within the 2 slides, ask again. Good. What do black box separations mean? I don't know if this slide might have come from Omer Reingold or maybe not. I don't remember after so many years. Okay, so this is the answer to your question. Almost all reductions in cryptography are black box, and in particular also relativizing. The basic, so there's one exception, although it appears in several places. The one big exception is zero knowledge for NP. Now, I didn't even define zero knowledge, but the point is every language in NP has a zero knowledge proof. How does it go? How do we prove it? We prove it for one specific language, like, I don't know, 3 colorability. And then to prove zero knowledge for another language, you need to do like a reduction, a Cook-Levin reduction, and that is highly non-black box, right? Because you look at the non-deterministic Turing machine computation, etc. So everywhere where I need to say, oh, there is a zero knowledge proof for this language. Well, first I'm going to reduce this language to 3 colorability, and then I'll use my zero knowledge proof for the 3 colorability. That step is not black box because I need to see the machine. So this comes up in some applications, like, I don't know, applications involving zero knowledge, like some, you know, taking secure computation from honest to malicious or some identification scheme. So there's some examples, but they're very, very few. Like all the examples I showed before on the big slide with the many things, they were all black box.
So zero knowledge would give you no black box constructions, right? I mean, the reductions.
You're saying the proof would still be
the adversary, you know, as a black box.
If your theorem is also that one-way functions imply that all NP languages have zero knowledge proofs, even the construction also uses the one-way function in a black box way, as long as you're not trying to prove anything.
okay. So you're agreeing with Vinod then that it's, but it's okay. So
2 different points actually.
I'm saying
that the reduction is black box.
there's reduction versus proof, and you are saying
Even
the
the
theorem
construction is
using the
black box.
one-way, but this might be important. Good. I'll repeat
So
what was said.
at that point, now we know better, but at that point, I think constant transient knowledge from one-way function required non-black box use of the one-way function. It's a mere paradigm. You're proving either you can invert this thing or that, or X is true.
Okay, so at this point, you're saying nothing is really deeply non-black box?
Today, actually, we have black box constructions from one-way function also, but at that point, all constant constructions actually were non-black box in the one-way function.
Okay, so I'll repeat both points separately because indeed they're different points. One point, I'll start with the point of what I said and Vinod corrected. Let me say it in this way. If I want to use the fact, I don't know how I proved it. It came from heaven that every language in NP has a zero knowledge proof. I guess I need to see how to do it. Okay, actually, I need both points are related to each other. Think about it. You have to use both of them. Anyway, there's a theorem that if one-way functions exist, then 3 colorability has a zero knowledge proof. That's the theorem. If there's one-way function, then 3 colorability has a zero knowledge proof. Okay. Then from this, I can conclude that every language in NP has a zero knowledge proof by Cook-Levin reduction. Both of these steps have something that might seem non-black box about them. The first step is like, you know, how do you prove that theorem that one-way function implies zero knowledge for 3 colorability? How do you use the one-way function? Do you use it in a black box way or not? Okay, so today we know how to use it in a black box way. The second part is I want to prove zero knowledge not for 3 colorability, but for my language, and that requires a reduction. That reduction is not black box because it uses the non-deterministic Turing machine. But this is less important. As I said before, the proof is more important. That was Vinod's point, am I right? The proof is more important. And the proof is black box in any case. So there's no good examples right, of non-black box. So I guess the answer to you is basically everything is black box.
No, but like now everything
Constant
uses
round
Garbled
public
circuit.
coin.
Sorry. Yeah.
Constant round public coin zero knowledge is still, we still know.
No,
only-
I think we can, like, that's the construction will look like, we can do it black box.
I mean, that makes this black box separation much more interesting.
But,
Even.
no, but yeah, but right now, like, all these new constructions of like IO, like,
sure.
they're all, everything that uses garbled schemes.
Good. I forgot. I had a sentence about it even here. Yeah, oraculated separations.
Even cryptography and zero, I think, is a garbled.
So, but all these are examples of constructions that.
Yeah, but that's what she, like, when she says black box, she means fully black box, which is.
Well, I defined it to be fully black box, but the most important part is the proof, really.
Well, how about cryptography and MC0? That seems very non-black box.
It's again,
Construction
the
is
construction is not black box, yeah.
But the proof is a black box. You take an adversary.
Exactly, yeah.
Converts it. I use the adversary as a black box.
But IR, it's not known how to do that for only black box reduction. It really relies on the construction being black box.
So you're saying there could be a construction of public encryption from one-way functions, where the construction is
uses garbled schemes, yeah.
non-black box, but the proof is still black box.
Yeah, that's a great open question. Like it's.
You think great open question in the sense that it's likely to be solved
So
in
Dana
this
actually had a
semester?
very nice. Dana has a nice kind of like conditional non-black box black box separation where the construction is allowed to be non-black box, but it's conditional and it's very partial, and so it's very hard.
Maybe we can solve it this semester.
I think Sanjay Mittal had another result that said
It's about compression
Darwin
too.
cannot solve this problem.
Yeah, so it's Kolmos.
Formalizing what that means. So you really need to invent a new non-black box construction that.
Could you repeat the question again?
Yeah. So the point here is that there could
Thank
be
you,
a
by the way. I love this.
from one-way functions, which where the proof, the reduction is black box, but the construction is not black box. That seems totally open. That's the point. But there are negative.
It's a very limited negative.
Very limited negative results that say, well, maybe not.
And when you guys are saying garbling schemes, that means like using IO or something.
No,
Let's say IO for a moment.
but garbage
So
means
make
you
it
can
the
get from one
garbling are
function.
not
It's Yao.
not black box.
Right.
Just look at the gate by gate by gate of the
So are there any examples of the proof is in black box? Any interesting examples?
where the proof is not black box.
Barak.
Yeah.
Barak, the simulator is not black box.
So yeah,
It's not. It doesn't fit in this therapy.
no, like Barak doesn't directly, but then if you use Barak as a building block to build something else, like non-malware commit or secure constant and secure computation and so on, then you do want a reduction, and the reduction uses that simulator in its belly. So therefore, so there are non-black box reductions that uses this zero-knowledge simulation technique.
It's a great.
What is the proof not black box?
The reduction. You want to say any attacker that breaks the scheme can be used to invoke the one function.
Remember that picture that I had, like when I tried to find it again.
And so then you can use the attacker. You can use the code of the attacker. That's what Barak's technique shows.
I know the hour is up, but let me stop at a reasonable stopping point, and we'll still have half an hour off, okay? Which will be very soon. Okay, this is about what the meaning of it. I think my favorite one is the bottom point. If you have a black box separation, it really gives you insight if you want to construct. That's what I like the most about black box separation. If you want to construct one from the other, it gives you ideas of what not to try and where yes to go. Good. So I wanted to say, and I forgot who asked this, Valentin, or somebody made a comment about things being equivalent. So in fact, all of this is highly non-equivalent to each other. And all of these separations are known. And in fact, it was hard to draw, so I didn't draw. But even early on, Rudish proved that key agreement in K rounds is separated from key agreement in K+1 rounds for any K. So they're in fact infinite. So what I just said about Rudish, that already shows an infinite hierarchy. But these incomparability results show there's not even, it's infinite and it's not a hierarchy even, they're incomparable worlds. Okay, so like there's infinitely many incomparable worlds in Cryptomania, like these are all, so remember I promised you all the colors. All of these are possible worlds, so it's like a big mess. Okay, I think this is a good stopping point. Right, it's beautiful. You see what I meant in the beginning? Good, so let's take a break and then I'll continue. I have a little more to say about these worlds. I didn't say anything about obfuscation, but I also wanted to talk about some open problems later that are not from this era, but from newer ones. Oh, I'm in time. I thought I was late. I'm just in time. I can take questions now or later or whatever you want.
I mean, there's a question about relativization, which is that if you don't get to the next couple of slides.
I won't get to know. Ask.
Yes.
What's the question?
Non-relativizing.
So everything that is all this discussion with Raphael right now, everything that's non-black box is non-relativizing. Because, is that true? Sorry, it's the opposite.
Yes.
A black box implies relativizing. Yes, no, I see. I don't know of any example. Your question does make, what I said is wrong, but your question makes sense, but I don't know.
Space equals zero knowledge and one
No, I think it's, Raphael, do you know? I think that there's no example of something that's yes, black box, but
Maybe
not
these like
relativizing.
de-randomization-based constructions, right?
Which ones?
Like for example, showing that you can de-randomize malware commitments with circuit lower bounds. Maybe you call this a non-relativizing construction. I'm not sure.
I don't know. You saying, but it is black box, but not relativizing?
I would consider it black box. You use a PRG to generate some randomness. Yeah.
But you would consider it non. I don't know the answer. That's interesting. I thought there were no examples like that, but I actually don't know.
Oh, I know that Aronson-Wilson showed ZK theorem is algebraizing, but it doesn't seem relativizing.
Yeah.
And
like Yanni said, like we don't know how to get zero knowledge for if you have an oracle, right? So you cannot give zero knowledge for MP to an oracle. So zero knowledge is highly non-relativizing.
But it's also not black box.
But what was the question? If you know something that's black box, but not black box implies relativizing. So
yeah, so that's just
so maybe it was the opposite. If it's black box, it's relativizing. You were asking something that's not black box.
I'm just confused.
And yes, relativizing.
Because on the one hand, it's sort of it seems like it's not relativizing in some sense, but it's also black box in some sense. So, yeah, it's just.
Right, you have to ask black box and what? It's not.
Yeah,
it's not
exactly.
black box in the entity language that you want to prove.
Exactly. Yeah. Good. That's the right answer.
The theorem is black box in the one-way function. You just use one-way functions to build commitments. The proof is black box. The proof is black box. But then when you use zero knowledge, that's when it's not.
Right, because you look at the circuit.
Good. Good time.
Okay, it's a good
Yeah,
time to
let's
stop.
continue.
We'll talk more later.